Today we're going to take a look at lesson 3.2, adding, subtracting, and multiplying polynomials. Later on in this chapter, we'll get into dividing polynomials, but adding, subtracting, and multiplying, this lesson basically serves as kind of a review because this is something you've been doing for a while now. So this is nothing super new for a lot of people. So example one, there's a few things we're going to cover, especially when you're adding and subtracting polynomials. You have to have what they call like terms. So when we get to that, I'll kind of emphasize exactly what a like term is because a couple things have to be present for you to add or subtract things. But when it comes to multiplying and dividing, we're not looking at dividing in this section, but when it comes to multiplying, it's game on. You can multiply any term by any term. There's no restrictions. You can multiply unlike terms times each other. It's when you're adding and subtracting, you have to have like terms in order to combine them together. Multiplying, you can do anything. So for example one, add and subtract polynomials. How do you add or subtract the polynomials? Well, kind of like I said, you have to have what they call like terms. So let me just emphasize what that is. A like term has to have two things. So it doesn't matter what you're looking at, what polynomial, what terms you're looking at. It has to have, in order for you to add or subtract them, you have to have the same variable. I'm going to put variable or variables, right? Because sometimes you'll just have x's. Sometimes you'll have a term that's like 3xy. You might have multiple variables. But in order for you to add like terms, they have to have the same variable or the same variables. And then those variables have to have the same power. So same variables to the same power, those will be like terms. So let me give you a few examples here. If I do something like 3x cubed plus 4x cubed, I can do that, right? They're both x's, they're both to the third power, so I can add these together. That gives me 7x cubed. So if I'm adding x cubes to x cubes, I'm going to still have x cubes. Notice that those exponents don't change. If I'm adding x cubes to x cubes, I'll end up with x cubes. Something like 4xy plus 2xy, right? Those are like terms. It's an x to the first and a y to the first. This is an x to the first and a y to the first. I can add those together. So when I do, I get 6xy. Again, if I add xy's to xy's, I still have xy's. Let's look at some cases where they are not the same. How about 7a squared minus 4a? All right, these are not like terms. Sure, they have the same variable, but they have different powers. This is a squared, this is a to the first. So I cannot combine those. They just stay two separate terms. It's like adding apples and oranges, right? Here you're adding apples to apples. Here you're adding apples to apples. Here you're adding apples to oranges. They're two totally separate things. So I can't add them together. So maybe something like, 4r s cubed minus 8rs squared. I don't know, right? I cannot do this. These are not like terms because in order for me to add these two things together, I have to have an r to the first and an s to the third. This is an r to the first, but that's an s to the second. These are not like terms. I can't add them together. They just stay separated like that. All right. So like terms, same variable to the same power. I can add them together. If they're different variables to different powers, I can't do anything with them. So here's an example that they're walking you through that. They're color coding them as well. So all my x cubes are red, all my x's are blue, my x squareds are green, and it looks like the constant is purple. So notice that they're putting the x cubes all in red, so then I can add those together. They're putting the x's in blue, so I can add those together, but in this case, there's only one x. The x squareds are green, so I can add those together, and then the constants are purple, so I can add those together. Notice that reds add to reds, blues add to blues, greens add to greens, purples add to purples, but I can't add a red and a blue or a red and a purple. Notice they're still separate terms here. So just make sure, keep that in mind. Same variable to the same power, I can add them together. This B example, it's a little more kind of involved, right? This is algebra 2, so it should look a little bit nastier, but just keep in mind that same property, same variables to the same power. So when I'm looking at this term right here, 3x squared y squared, I can add that to any other x squared y squared term, okay? This is an x y squared, so I can't add that to this term. This is just an x squared, so I can't add those two together. Here's another x squared y squared, so I can add those two together, right? No other x squared y squareds. So just be careful, make sure it's the same variable to the same power, and you should be good to go. I want to emphasize one more thing here, and this is a common mistake that a lot of people make. In part A, notice that you're adding the second polynomial here, so you're just adding each of these things, right, to the first polynomial. Here in part B, you're subtracting that second polynomial. So you're subtracting 2x squared y squared. You're subtracting 3xy squared. You're subtracting negative 2x squared. Be careful with that. Make sure that you're subtracting all of these things because your signs could get mixed up and then you're not going to have the correct polynomial at the end. Hopefully you're saying to yourself, that makes a lot of sense. We've been doing that for years, right? Not too complicated. Example 2, now they're talking about multiplying polynomials. So here's how you multiply them. Part A, this is an example of a binomial times a trinomial. Lots of people do different things here. It's kind of up to you. I usually just kind of take that first term and I multiply it through the second polynomial. And then I take the second term and I multiply through the second parentheses, and then I just add like terms at the end. And that's what essentially they're doing here. Notice they're taking the first term, 2m, and they're multiplying it by that second set of parentheses. So you're just going to distribute 2m, bam, bam, bam. And then you're taking that second term, which is a 5, and you're still going to multiply it by that second set of parentheses. So you'll distribute it. 5 times 3m squared, 5 times negative 4m, 5 times 2. Once you distribute the 2m, once you distribute the 5, you'll have this step right here. Now at this step, this is the part where I'm basically going to do example 1. I'm going to add and subtract like terms. So I can add any m cubes together. I can add any m squareds together. I can add any m's together. I can add any constants together. Will you always be able to add things together? No, it just depends on the problem you're given. But add what you can, same variable to the same power, add them together. In this case, it looks like there's only one m cubed, so that should stay by itself. I've got a couple of m squared, so I can add them together. I've got a couple of m's, so I can add them together. And then just a constant, so I can't do anything with that. So for part A, when you're doing something like a binomial times a trinomial, I would take that first term, the red term, multiply it by that second set of parentheses, distribute, right? 2m times 3m squared, 2m times negative 4m, 2m times 2. And then make sure you're going to add it to that second term multiplied by that second set of parentheses as well. B looks a little more complicated, but you're just taking it in multiple steps. So what I would do is I would ignore mn plus 4. And I would just multiply those two binomials together. Mn plus 1 times Mn minus 2. So some people have learned like the FOIL method, but it's the same thing you did with part A. I would take Mn and multiply it by Mn minus 2. I would take 1, multiply it by Mn minus 2. And let's see how they did this, which is exactly what they did. They did Mn times Mn minus 2, and then they did 1 times Mn minus 2, and they got that first set of parentheses right there. Now that you have that, you can combine any like terms you have. In this case, they have 2 Mn's, so they added those together. Now you're back to part A, where you have a binomial times a trinomial. So again, I would take MN and multiply it by that first set of parentheses. Then I would take 4, multiply it by that first set of parentheses, and then combine any like terms you have for your final answer. I'm going to walk you through some of these steps or some of these problems anyways when we get back to the practice section. So I'll write them all out for you. But if you want to walk yourself through those examples, that's a good idea. Understand closure. Is the set of polynomials closed under addition and subtraction? So what they're saying, communicate precisely. Can you think of 2 real numbers? So this is just kind of something else. The set of real numbers is closed under addition. If A and B are real, then A plus B equals C. C also must be real. So remember back a while ago, we talked about real versus imaginary numbers. Imaginary numbers come from something like when your discriminant underneath the square root sign was negative, you're dealing with imaginary numbers there. I don't want to get too far into that, but that's where that comes from. A real number is basically like -1 or 1/2 or something like that. If I add real numbers to real numbers, I should get a real number. It's not going to produce an imaginary number. Okay. So here are kind of two generic algebraic definitions. Looking at this can really be confusing. So I don't want to dive too deep into this example here, but just kind of understand that idea where if I add a real number to a real number, it's going to give me a real number. Okay. When you're looking through this example, there's certain ways to read this. Like you read this a sub n and then x to the nth power. So a can be any number, n can be any number, x is my variable, and then n, that exponent, could be any number as well. And what they're doing here is they're just reducing that number, that sub number and that exponent number each time they move down the line. So what they're emphasizing here is that this polynomial is in standard form. That's all they're trying to say. Really confusing way of looking at it, just to say it's in standard form. So again, don't get too caught up with this example. Just kind of keep that in mind. When I take a real number and I add it to a real number, it's going to give me a real number. Example 4. Write a polynomial function. Carolina makes wind chimes to sell at the local street market. As Carolina produces a greater number of wind chimes, she can lower the price per unit. The function v of x relates to the price v to the numbers produced x. The cost c of making x wind chimes can be presented by this function c of x. How many wind chimes could Carolina sell each week to maximize her profit P? So just based off of giving you those 2 functions, you can kind of set it up and do some calculations to figure out what that maximization, function would be, P of X. Let's go ahead and take a look at that. So they give you 2 functions. This first function, V of X, relates to the price. And then the second function, C of X, relates to the cost. So basically, one thing is going to be the revenue or the profit function, and then the other function is going to be the revenue function. So that V of X, that's going to be my profit function. So if I take the function that they give me, and I multiply it by the amount of chimes that I want to sell, that's going to give me the total amount of profits. And then the other function, C of X, that's going to be the cost to make these wind chimes. And again, if I take that and multiply it by the amount of wind chimes that I sell, that'll give me the cost that it will take me in total to produce all these wind chimes. So write a function for revenue R by multiplying the price V of X of each number by X. So again, that's just the number of chimes that you're selling. So that's where they're getting R of X. They're just taking the function V of X that they give you in the problem and they multiply it by X. Because if this function 48 minus 2X is going to give me that revenue that I'm going to create, well, that second X is just telling me I'm selling this amount of wind chimes. I need to know how many wind chimes I'm selling in order to figure out what that revenue is going to be. Then they're showing that you're subtracting 2 functions. That kind of makes sense. If you are basically, spending money in order to create these things. You're going to have to subtract the amount of money it takes to create and to produce these wind chimes in order for it to tell you how much profit or how much money you're generating. So you want to take that, subtract that, the amount that it takes to make the wind chimes from the total amount of money you're making, the revenue, which will tell you that profit that you're trying to make. So kind of a confusing way to set that up, but now that it's set up, you're just going to take those two functions and simplify, right? Just keep in mind PEMDAS, right? Parentheses, exponents, multiplication and division from left to right, addition and subtraction from left to right. It's a very simple idea. We've talked about it for years, right? The idea of PEMDAS, the order of operations. But if you forget the order of operations, it's going to send you down the wrong path. So make sure you're always following that. So my profit function is going to be 48 minus 2x times x minus that cost that it takes to create these wind chimes. All you have to do is follow PEMDAS. So inside my parentheses, I can't subtract those two numbers because they're not like terms. Inside this parenthesis, I cannot add those two numbers because they're not like terms. So now I move to exponents, right? Parentheses, exponents. There are no exponents. So now I'll go from multiplication and division from left to right. You've got to go from left to right. So the only set of multiplication, well, there's a couple here. The first one is this x. I'm multiplying that first set of parentheses by x. So essentially what I want to do is distribute that x. X times 48 is 48x. X times negative 2x is negative 2x squared. You heard me say that there was a couple sets of distribution, a couple of things of multiplication here. Here's the second one. I am subtracting this entire second set of parentheses. I don't want to just subtract 12x. I want to subtract 64 as well. So think about this subtraction as distribution as well. Negative 1 times 12x is negative 12x. Negative 1 times 64 is negative 64. Again, that's a common place that people make mistakes. What they do is they do this. They go subtract 12x, which is there, but then they'll just put plus 64 here, right? Keep in mind, you're subtracting the 12x and you're subtracting the 64, right? Don't lose that sign. Now I can combine like terms to give me that final quadratic right there. So if this is her profit function, you can go to Desmos. You could type that in the graphing calculator or in the graphing portion of Desmos, which is what I would highly encourage you to do. Looks like they're giving you a little picture here off to the right. If I went to Desmos and typed in that quadratic, I'd get this parabola right here. And what that means, that local minimum or that local maximum, that maximum part, the tallest part of that parabola, what that's saying is if I sell 9 wind chimes, I'm going to have a profit of $98. So if I sell less wind chimes, I'll have less of a profit. If I sell more wind chimes, I'll have less of a profit. There's always that sweet spot with selling things because you don't want to sell something super cheap if it's a good product, but you also don't want to sell something really expensive if it's a crappy product. So there's always that sweet spot. So if I sell 9 wind chimes, I'll make $98. Example 5, we're on page 142. Compare two polynomial functions. Carolina's profit function, so this is kind of based off of example 4 that we just talked about. Y equals P of X is represented by this graph right here. Kayo's profit from selling X flower pots can be modeled by the function shown. So again, you could go to Desmos if you want to and type this in the Desmos graphing calculator and you can kind of get a visual representation of both of those situations. So I'll try to leave that up there. Part A, find the y-intercept of each function. Who would lose more money if neither person sold any items? So the y-intercept here, they're just giving you off of that graph is 0, negative 64. So if I don't sell any items, I'm gonna actually lose money. I'm gonna lose $64. If Carolina doesn't sell any items, she'll lose 64 bucks. Like I said, Kayo, you can go to Desmos and type that in, which is what I would do. Sometimes it's a lot easier to kind of pull information from a graph. You could also do this algebraically though. If you want to find out what the y-intercept is, you basically want to know when your x values are 0, right? Take a look at this Carolinas, right? X is 0, y is negative 64. So as long as x is 0, you'll figure out what the y-intercept is. So r of 0 equals 0, parentheses, 0 minus 3, parentheses, 10 minus 0. So if you do the math, you know that 0 times anything is going to be 0, right? 0 times anything is going to be 0. So we can still go ahead and go through this though. So inside each set of parentheses, 0 minus 3 is negative 3. 10 minus 0 is 10. Well, 0 times negative 3 times 10 is just going to be 0. So with Kaio's flower pots, it's a different story. Carolina, if she doesn't sell any, she's going to lose money. Kaio, if they don't sell any, they're not going to lose any money. They're not going to make money, but they're not going to lose money either. So if I go to Desmos and graph this function right here, the y-intercept would be 0, 0. Interpret the end behavior of the functions. So if you take a look at Carolina's wind chimes, the end behavior, which is basically not concerned about anything in the middle, it's just these endpoints, right? What's happening to my function. The end behavior looks like it's going down into the left forever and then down into the right forever. Okay. So what that's saying is if I sell, you know, all the way from 0, you know, all the way to infinity wind chimes, what's going to happen is after I sell, what does it look like? After I sell 16 wind chimes, I'm not going to make any money, no profit. But once I sell more than 16 wind chimes, so 17 or more wind chimes, I'm always going to lose money forever. I'll never stop losing money. There'll never be a point where I sell more than 16 wind chimes and make money. The flower pots is a different story. Let's take a look at this. If I multiply this all out, I'm going to go ahead and do that real quick. See what we get. So if I multiply this out, I'm going to get x minus 3, 10 minus x. So I'm going to multiply the first two factors together. So I'm not going to worry about the 10 minus x. So if I multiply the first two, I'm just going to distribute that x. So I'll have x squared minus 3x. Now I'm going to go ahead and multiply this binomial times this binomial. So I'm going to take x squared, and I'm going to multiply it by that second set of parentheses. So this times this. And then I'll take that second term, negative 3x, and multiply it by that second set of parentheses. And let's see what we get. X squared times 10 is 10x squared. X squared times negative x is negative x cubed. Negative 3x times 10 is negative 30x. Negative 3x times negative x is positive 3x squared. So if I add like terms, write this in standard form, the x cubed is going to come first. I've got a couple of x squareds. I can add those together. So that's 13x squared. And then I've got that negative 30x here. So overall, this is a negative function. The highest degree is a 3, so it's a negative odd function. And if you look back in your notes from, what was it, 3.1, every negative odd function is going to start off going up and to the left and end up going down and to the right. The stuff in the middle is going to change. There might be some wiggles, bounces, right? Doesn't matter. But the end behavior, it's always going to go up and to the left, down and to the right. And I think we're supposed to interpret this. So what that's saying is basically if you're selling flower pots, you can't sell negative flower pots. So all that stuff is just garbage. But at a certain point, you will lose money after that x-intercept. What are my x-intercepts? 0, 3, and 10. So after 10 flower pots, I will always lose money. On page 143, we have our concept summary, talking about just the idea between adding and subtracting like terms. I think they separate these, even though technically subtraction is addition. What they really want to emphasize is when you're subtracting that second polynomial, make sure you're subtracting every term. You're subtracting 4x cubed. You're subtracting 4x squared. You're subtracting -8, right? That's really key. Then with multiplication, they're just going through another example here. Take that first term x, multiply it by that second set of parentheses. Take that second term 5, multiply it by that second set of parentheses. Combine any like terms you have, and then write it in standard form at the end.